Parentheses. The role of parentheses is to indicate priority and help avoid ambiguity. For example, left parenthesis A and left parenthesis B or C right parenthesis twice is quite different from twice left parenthesis A and B right parenthesis or C right parenthesis, not only in appearance but also in meaning. The former is a conjunction, while the latter is a disjunction. For this reason, we have not allowed propositional formulas of the form A and B or C. Also, A implies B implies C would be utterly ambiguous. With proper use of parentheses, this should be either left parenthesis A implies left parenthesis B implies C right parenthesis twice, or left parenthesis twice A implies B right parenthesis implies C. Other ambiguous formulas, results of wrongful omission of parentheses, are A implies B and C, and A or B implies C. However, some parentheses are unnecessary. The definition of propositional formulas produces more parentheses than is in practice necessary. Therefore, we make the following convention about parentheses. Parentheses are left out unless necessary for unambiguous reading. Accordingly, A and B and C means either left parenthesis twice A and B right parenthesis and C right parenthesis, or left parenthesis A and left parenthesis B and C right parenthesis twice. Similarly for A or B or C. The reason why it is usually not necessary to make a distinction between left parenthesis twice A and B right parenthesis and C right parenthesis and left parenthesis A and left parenthesis B and C right parenthesis twice is that when we learn to assign meaning to propositional formulas, we see that these formulas have the same meaning, which is, intuitively speaking, that A, B, and C are all three true. If, for some special reason, it is necessary to emphasize whether we are talking about left parenthesis A and B right parenthesis and C right parenthesis, or left parenthesis A and left parenthesis B and C right parenthesis twice, we can do it by leaving the parentheses where they are. We also often leave the outmost parentheses away for simplicity. Here are some examples of propositional formulas. A disjunction, P0 or P1. This is just about the simplest propositional formula we can think of apart from the proposition symbols alone. Note that we have left the outmost parenthesis away according to our convention. So officially this is the formula left parenthesis P0 or P1 right parenthesis. Our second formula is an implication between a disjunction and an atomic formula. Left parenthesis P1 or P2 right parenthesis implies P3. Intuitively, this formula says that if either P1 or P2 is true, then so is P3. But we have not yet defined the meaning of propositional formulas. Until we do so, we assign to this propositional formula just an intuitive meaning coming from the everyday use of the words or and if then. When we do define the meaning of propositional formulas in mathematical terms, it turns out that the meaning reflects our everyday use of the words or and if then pretty well. But there are also some surprises. But we are getting ahead of ourselves. A negation of a disjunction. Negation left parenthesis P1 or P2 right parenthesis. Intuitive meaning of this formula is that it is not the case that P1 is true or P2 is true. Note that in spoken language we do not use parentheses, but we indicate with intonation what we mean. If the formula was not P1 or P2, the intuitive meaning would be that it is not the case that P1 is true or P2 is true. Something that could be said a bit clearer as either it is not the case that P1 is true or else P2 is true. Here is a conjunction of an atomic formula and a disjunction of two atomic formulas, namely P0 and left parenthesis P1 or P2 right parenthesis. When we read this formula, we also read the parentheses. Also, when we say the intuitive meaning, we may have to add explanatory words because intonation is not sufficient. So we can say, the intuitive meaning of this formula is that P0 is true and, in addition, either P1 or P2 is true. Now we have a negation of an implication. Negation left parenthesis P3 implies left parenthesis P2 implies P1 right parenthesis twice. The intuitive meaning of this is that it is not the case that if P3 is true, then if P2 is true, then P1 is true. Let us not pretend that it is easy to discern what this really means. Both implication and negation are rather complicated operations, and when they are combined and iterated, one really has to take paper and pencil to calculate the exact meaning, something we learn to do later on this course. Here is a disjunction of four formulas. Left parenthesis P0 and P2 and P5 right parenthesis, or left parenthesis not P1 and not P3 and not P4 right parenthesis, or left parenthesis not P1 and not P4 and P5 right parenthesis, or left parenthesis P0 and not P3 and P4 right parenthesis. These kind of disjunctions, even quite long ones, are common in industrial uses of logic. This could be, for example, a condition under which a car engine has to switch itself off. There are a number of situations described by the disjunct in which the car engine has to switch itself off. If just one of the disjuncts happens to be the case, the engine stops. The meaning of the proposition symbols would be propositions of the type thermometer indicates overheating, air intake is blocked, parking brake is pulled, etc. Our last formula is a conjunction of four formulas. Left parenthesis P0 or not P1 or P2 right parenthesis, and left parenthesis P1 or not P5 or not P6 right parenthesis, and left parenthesis not P1 or not P4 or P5 right parenthesis, and left parenthesis P0 or P3 or P4 right parenthesis. This type of conjunctions, again possibly quite long, are typical in industrial applications, just as the above disjunctions. An example could be a safety condition for a train to keep moving. There are a number of conditions, each one of which has to be satisfied for the train to be allowed to keep moving. The meanings of the proposition symbols would be propositions of the type: a proceed signal is green, a proceed signal is yellow, a proceed signal is red, cap signal is green, crossing warning signal is red, the speed is over 80, etc. Let us now focus on the simplest propositional formulas, the proposition symbols, and discuss in detail what are they for and what can they do for us. Recall that the proposition symbols are denoted P0, P1, and so on. They denote basic states of affairs which can be true or false, such as it is raining, the lamp is lit, 4 less than 10, x less than 10, the door is closed, the train is moving, the switch is on, I am in Rome. In all the above examples, one cannot further analyze the sentence in terms of propositional operations. Simply put, the words not, and, or, if then, and if and only if, do not occur in them. The act of giving states of affairs, such as the above, a name, such as Pn, is very much like denoting the speed of an object by v, the mass by m, or denoting the length of a trip by a, and time spent by t. The only difference is that the proposition symbols P0, P1, etc. do not denote magnitudes like speed, mass, etc., but states of affairs, whether something holds or not. This is the difference between logic and mathematics in general. In logic, the fundamental concept is that of a proposition holding or not holding, being true or false. In mathematics, the fundamental concept is that of a magnitude, something that can be measured, typically by real numbers. In the mid-19th century, George Boole made the momentous invention that propositional logic can actually be seen as the mathematics of the numbers 1 for true and 0 for false. Negation. The negation of A, not A, is intuitively simply the denial of A. Here are some examples. Negation, it rains, means it is not the case that it rains, or it does not rain. Negation 4 greater than 10 means 4 is not greater than 10. Negation the door is closed means the door is not closed. In natural language, negation is not as simple as in the formal language of propositional logic. In propositional logic, if we want to deny a sentence, we just put the negation sign in front of the sentence. Not so in natural language. In natural language, you have to find the proper place for the negation. It would perhaps be understandable if we said, it is not the case that the door is closed. But the door is not closed is how it is said. Note that the negation of negation, the door is closed, is negation, negation, the door is closed. If we denote the door is closed by P0, then negation, the door is closed, is negation P0. And negation, negation, the door is closed, is negation, negation P0. We may have the temptation to give negation, negation, the door is closed, the intuitive meaning, the door is closed, because we may think that the negations, so to speak, cancel each other out. This is how it is in natural language. If I say the door is not closed, and you say that actually that is not the case, we both realize that the door is indeed closed. However, we are making here already logical conclusions. If we abstain from logical conclusions, negation, negation P0 is what it is. A proposition symbol with two negations in front of it. Only when we define meaning of propositional formulas, we may conclude that negation, negation P0 and P0 have the same meaning. That is an important point, because we could also choose to define the meaning of negation somewhat differently, as is done in so-called intuitionistic logic. And then negation, negation P0 and P0 would not have the same meaning. The conjunction of A and B, denoted A conjunction B, says intuitively that both A and B hold. The sentences A and B are called the conjuncts. So, a conjunction A conjunction B is the conjunction of two conjuncts. Here are some typical conjunctions. It rains and it blows. 4 less than 10 and 7 less than 3. The door is closed and the train is moving. Conjunction is the easiest of our logical operations. It is really unproblematic, and we quickly move to disjunction, which provides formidable challenges.